Colligative properties. We always talk about colligative properties when we talk about solutions because they are the effect of different things happening to a solution. A colligative property is defined as a property of a solution that's dependent on the number of solute particles, but not the entity of those particles. So it doesn't matter what the particle is, okay? It just matters how many particles are present. We will consider 4 colligative properties. We're going to talk about vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. But again, all of these things depend on how much of something is present, but not what is actually present. First up, let's talk about vapor pressure lowering. The first system I'm going to talk about is a non-volatile solute in a volatile solvent, okay? I'm not going to talk directly about an example with both volatile species. It works just like Dalton's law of partial pressures. When you learned about gas laws, they each have their own mole fraction. They each contribute to the overall system the same. So I'm not going to talk about that, but there is examples like that in your notes. I want to talk more clearly, though, about the vapor pressure lowering, which is caused by that non-volatile solute in a volatile solvent. So again, volatile means that it has a vapor pressure. What that means is that if left out in, regular atmosphere, whatever it may be, the species will go into the gas phase without actually boiling. So that means if I take a glass of water and I spill it on the floor, even if I don't clean up that water, the water will evaporate away, even if it doesn't reach 100 degrees Celsius. Okay? So the water will still evaporate away. It will still go into the gas phase, but it's never actually boiled. And that's because water has a vapor pressure. Water goes into the vapor phase. Again, vapor phase is when it's in the gas phase without actually being at the correct temperature and pressure conditions to do so. So in this case, I'm going to talk about volatile solvent. We're going to use water as the example because it's just easiest. It doesn't have to be water. We're going to use water. And then a non-volatile solute, we're going to just talk about, actually the example I'm going to use below is sugar or high fructose corn syrup, but we'll just say sugars. Okay? If I put sugar out on the countertop, it's not just going to evaporate away. So what happens is that the non-volatile solute actually prevents some of the volatile solvent from escaping the solution. And that's what the joke over here is about. Calm down and stop trying to evaporate. Non-volatile solutes lower your vapor pressure. Yes, sir. The water molecule is going to stay here. So the demonstration down here is what it's showing is I've got pure solvent over here, and I'm going to say that this is water, okay? And I've got a solution, and let's say this is some kind of carbonated drink. Let's just say it's Coca-Cola, or let's say Pepsi. I don't really care. My mother loves Pepsi. Let's say it's a Pepsi, okay? Over time, if I leave that container out, eventually all of the CO2 will escape first, and the Pepsi will go flat. But eventually, most of the Pepsi will escape as well. But what's going to be left behind? So let me back up. What's happening here? If I have pure solvent, if I just have water in here and I have a tube of water, eventually all of the water will escape, and this will just be an empty tube left behind, right? But the one that has the solution, if I leave it for the same amount of time, what's going to be left behind is a sticky residue. What I want you to think about is you go to a drive-thru. You order some kind of drink, some kind of carbonated, sugary drink. Doesn't even have to be carbonated, just sugary drink. They give it to you in the drive-thru window, but when they filled it in their machine, it got drops of the liquid that you're going to drink on the outside of the cup, and nobody has wiped it off. And you don't think about it, and you just take it and you just put it in your cup holder, okay, in your car. A week later or so, you go to pick something up out of that cup holder, and you realize it is now sticky. It's sticky because the water that your drink was comprised of, the bulk of the liquid of that solution is water. The water has evaporated away. But what's left behind is these sugars that are now sticky. But sugar itself isn't normally sticky. It's sticky, though, because it's trapped some water molecules behind with it. Not all of the water has evaporated. So the water evaporates, but a couple of those particles are stuck behind. Those couple of particles stuck behind are making that sugar wet and hence sticky to you. So some unevaporated water molecules are present with a very high concentration of the solute. To do the math here, we use Raoult's law. Raoult's law is a derivation of Dalton's law of partial pressures, okay? It looks just like Dalton's law, but the partial pressure of the component you're looking at, which is your volatile substance, so the partial pressure of A in this case would be the partial pressure of water, is equal to my mole fraction of water, so how much of my original system was water, times the pure vapor pressure of water. So this means the pure vapor pressure. The pressure of my overall solution is equal to the mole fraction of that volatile substance times the pure vapor pressure of that volatile substance. Because only the volatile substance is the one escaping, it's the only one contributing to the pressure of the solution. Okay? So it works the same as Raoult's law. Let's work an example. What is the vapor pressure of an aqueous solution formed by dissolving 20 grams of glucose, C6H12O6, a non-volatile non-electrolyte? I'll talk about both those terms in just a sec. In 100 grams of water at 25 degrees C. I'm told that the vapor pressure of pure water is 23.756 torr at 25 degrees C. Okay. This should say non-electrolyte in front of it. I need to fix that in my slides, and I did not catch that before. I apologize. It should say non-electrolyte. We'll talk about electrolytes and non-electrolytes in just a bit, but it is important to know it's a non-electrolyte, okay? Non-electrolyte means that it just stays together as one particle in solution. Sodium chloride is an electrolyte. It breaks apart into sodium ions and chloride ions. That's also important, but we're going to deal with that after we learn the colligative properties. Non-volatile means that it is not going to escape solution, okay? So it's not going to contribute to the overall pressure of the system, but it does contribute to how many particles I have in solution. So in this example, water is volatile. I know that because I know water has a vapor pressure. Why do I know? It tells me here that the vapor pressure of pure water is this at 25 degrees C. I have to be given that information. I don't know the vapor pressures by heart. That's not something you'd have to memorize. If I tell you that's a vapor pressure, it means it is volatile. Glucose is not volatile. So when I look at my thing, my pressure of my solution is going to be equal to my mole fraction of water times my vapor pressure, pure vapor pressure of pure water. I need to figure out my mole fraction. So again, my mole fraction of water is equal to the number of moles of water divided by the total number of moles of the solution. Number of moles of water plus the number of moles of glucose. If I do the math here, number of moles of water, let's see, where is my water? I've got 100 grams of water. What is my sig fix there? 100.0 grams of water. I know 1 mole of water is 18.02 grams. This gives me 5.540 sig figs moles of water. I'm going to move my screen. I'll move it back down in a sec. If I look at the moles of glucose, C6H12O6, I have 20 grams of glucose. I know that 1 mole of glucose is 180.2 grams. Why do I know? Because I can add up the molar mass. And this is going to give me 0.110, 3 sig figs, so the 3 sig figs here, moles of glucose. Okay? So now I can plug those into my actual mole fraction up here. I know that I have 5.540 moles of water divided by 5.540 moles of water plus 0.110 moles of glucose. This gives me a mole fraction of 0.9805. based on sig figs. The addition below gives me, this number would have 4 sig figs to it, so 4 divided by 4 gives me 4 sig figs overall. Again, what mole fraction means is basically the fraction of that system that is that component. So in percentage form, this would mean that 98% of the solution is water, which means that my vapor pressure will be pretty close to the pure vapor pressure of water, but it will be lowered a little bit because there's some glucose molecules there that are holding back some of those water molecules. My pressure in my solution is equal to 0.9805 times my pure vapor pressure of water, which I was given, 23.756 torr. My pressure in my solution is 23.29 torr. Students often ask me, do I have to change the units into atmospheres? No, you don't. You're welcome to if you feel comfortable with that, but you don't have to. And personally, I don't encourage it because students are likely to make more mistakes by doing that than not. This didn't specify what the final pressure had to be, and I didn't have to use the ideal gas law, so I'm fine leaving it in torr. Let's work a conceptual example. 2 solutions. I've got 10 grams of C6H12O6, which is glucose, in 1 liter of water, and I've got 10 grams of C12H22O11, which is sucrose, in water. Which of the following is true? So again, glucose and sucrose. The glucose solution has the higher vapor pressure. The sucrose solution has the higher vapor pressure. Both solutions have the same vapor pressure, or there's not enough information to compare vapor pressures. So students are going to want to say D, but that's not actually correct. There is enough information here to actually compare vapor pressures. And they do not have the same vapor pressure. So what's a little, and this is confusing, but I want you to think about this conceptually, okay? I have 10 grams of each one. But this example is important because this example helps us remind us why we can't compare grams, but rather we compare moles. Because grams does not mean moles. Moles means number of things. The mole of 1 mole of water is not the same grams as 1 mole of oxygen gas. 1 mole of water is 18.02 grams. 1 mole of oxygen gas is 32 grams, okay? So we can't compare grams. This example is comparing grams, though. So what do we do with that? We think about their molar mass. This has 180.2 grams per mole. This one is 342.3 grams per mole. So you can do it conceptually or mathematically, technically, yes, but I want you to think about it conceptually. If I have 10 grams of each one, that means that I have more of these. I have more moles present. I have less moles here. Why? Because it takes more of these to reach 10 grams because it's a smaller compound. So lower molar mass is more moles present. In 10 grams of sample. Larger molar mass, sorry, I need to move the screen so I can write on it. Is less moles present in 10 grams, okay? If I got to reach 10 grams and it weighs less of it, I need more of them to reach that 10 grams. If I need 10 grams and the molecule itself weighs more, it's going to take less of them to reach that 10 grams. So with that in mind, what causes a higher or lower vapor pressure? Let's just say what causes a higher vapor pressure. Why am I saying higher? Because these say higher. I told you already that it's not D. It's not C. And this is why I'm going to explain why, how we can figure out which one is higher. Higher vapor pressure means it is easier for the volatile solvent to escape the solution. What would allow something to be easier to escape? Fewer molecules that are non-volatile holding it back. So what causes this? Fewer non-volatile molecules in solution. I know these are not the right numbers, but let's just pretend, okay? Let's say I've got 10 of these. I have 10 molecules present here, and I have 5 molecules present here. Again, these are not the right numbers. I know that. It's bigger than that, but let's just do it simplistically. Let's say 342 is about double 180. It's slightly off that. So let's say 10 molecules of glucose to 5 molecules of sucrose. Let's say each molecule can hold back 1 solvent molecule. That means that these 10 glucose could hold back 10 water molecules. These 5 sucrose could hold back 5 water molecules. Okay? Again, it doesn't matter what they are, it matters how many there are when it comes to colligative properties. So don't worry about everything else, it's how many are there. Glucose is going to hold back 10 water molecules, sucrose is going to hold back 5 water molecules. That means that the sucrose is allowing more water molecules to escape. More escaped, which causes a higher vapor pressure. So the sucrose solution has the higher vapor pressure. Because it has less particles present, therefore it allows more molecules to escape. So boiling point elevation and freezing point depression are the other 2 colligative properties we have. And to do these, you need to remember the definition of boiling point, okay? Remember that the definition of boiling point is the temperature at which the vapor pressure of a liquid equals the external pressure. The cartoons here are just to try to help guide you when you're trying to do the math on it. Friends keep you cool and friends keep you from freezing. Friends keep you cool. These guys make it harder for me to reach my boiling point. This is boiling point depression. Friends keep you from freezing. They lower your freezing point. This is boiling point elevation. Boiling point elevation, freezing point depression. I find it easier for students to remember actively that boiling point is elevated and freezing point is depressed. So that means the new boiling point is higher. The new freezing point is a lower value. Okay, and I say higher and lower intentionally because we often use water as solvent, but it doesn't have to be solvent. So it doesn't mean freezing point, if you're using water, will be negative, but if you're using something that doesn't have it has a freezing point that's positive value already, it may still be a positive value, but it will be lower on the scale. Also, just for ease, memorize these 2 equations, okay? The one above, I'll explain why it doesn't matter as much. The one above is for non-electrolytes, but the one below, the delta TB equals KB times M times I and delta TF equals KF times M times I, is always valid, and we can deal with I even when it's a non-volatile substance. So I recommend just ignoring the top ones and memorizing the second ones. What do these mean? This means that the change in boiling point temperature, which will be your boiling point of solution minus your boiling point of the pure solvent, is equal to KB, which is your boiling point elevation constant, M, which is your molality. Remember, molality is moles of solvent, moles of solute over kilograms of solvent. and I is your Van't Hoff factor, which we haven't talked about yet, but we will soon. Okay? The biggest thing is for that change in TB, this needs to be a positive number. I don't care if your boiling point is both negative. Your delta TB needs to be a positive number here. So take the bigger number, subtract the smaller number. Or remember solution minus solvent. Over here, delta TF, this is the freezing point of your pure solvent minus the freezing point of your solution. But again, biggest thing here, it needs to be a positive number. So I don't care if you remember which one subtracting from which, make it positive. Your Kf is your freezing point depression constant. M, again, molality. Moles of solute over kilograms of solvent. And I is your Van't Hoff factor. Okay? So let's talk about this actually conceptually, though. Why? Why does the solute raise the boiling point and lower the freezing point? So again, we reviewed the definition of boiling point. We know the temperature at which the vapor pressure liquid equals the external pressure is the boiling point. We know that delta TB equals KB times M times I. So based on this definition, the boiling point is a function of vapor pressure. The lower the vapor pressure, the higher the boiling point. Again, vapor pressure, how much is the pressure required, or the pressure of the solution or system when it equals the external pressure. So if I have a lower vapor pressure, that means less particles have escaped to make that pressure. The vapor pressure, again, is that pressure of the liquid above the phase that's escaped into the vapor phase. Lower vapor pressure, I have less particles in the vapor phase. In order to reach the boiling point, I need to add more heat into it to get them into that vapor phase. So it requires a higher temperature, higher boiling point. The vapor pressure of a solution is lower than the pure solvent. We just talked about vapor pressure lowering, how they hold back the pure, they hold back some of the solvent. The non-volatile solutes hold back some of that pure solvent. So more heat is needed to reach the external pressure, causing a higher boiling point. What I see on the graph over here, the green line here is your pure, I cannot draw even on a line. We're going to pretend that I can draw. Okay? The green here, the green here, the green going up here, that's your pure solvent. What I see here, this pinkish red line, is your solution. So I see the boiling point of the solution has been increased comparative to the pure solvent. But that's because, again, I need more heat added in to cause all of those particles to actually escape because they're being held back by the non-volatile solute in the solution. The freezing point depression, I see kind of a similar situation. The fusion curve, again, fusion means melting. The fusion curve of the aqueous solution is shifted to the left relative to pure water. So again, it doesn't have to be pure water. It doesn't have to be aqueous solution, but any solution. It doesn't matter what I'm doing. I see a lowering of the freezing point. Fusion is the separation between the solid and liquid phase on the diagram. So I'm gonna have to make it even colder to let it slow down enough. And it does deal with vapor pressure, but it gets a little more complex than that. But slow it down enough to let those the solute-solvent interactions really take over, locking that solution into its crystal phase. So I add a non-volatile solute, I cause my boiling point to increase, I cause my freezing point to decrease. This all leads back to vapor pressure. And you can see here some freezing points and boiling points of common compounds. Why do I care? Because sometimes you're going to need these in examples. So like benzene, its thermal freezing point is 5.5. Its Kf value, which is, again, Kf is your freezing point depression constant. Kb is your boiling point. elevation constant. Did I write that? Yeah, okay, making sure I wrote elevation. So I was just thinking about the fact that freezing point gets colder, boiling point gets hotter. Like, boiling is hot, so it gets hotter. Freezing is cold, so it gets colder. But if you ever need any of these values to do any of the examples, you can see them here. They would be provided to you if you needed them, okay? Let's see. Making sure I got everything written down here. Yes, okay. So, again, vapor pressure is lowered. So, at a given pressure, the temperature has to increase to reach the new vaporization line. At a given pressure, temperature must decrease to reach the new fusion line. Okay. Okay, so let's go ahead and work an example with a boiling point elevation so you can kind of see how we can apply this. A solution of an unknown, non-volatile, non-electrolyte was prepared by dissolving 0.250 grams of an unknown in 40 grams of carbon tetrachloride. The new boiling point was 76.97 degrees C. What is the molar mass of the solute? Kb is equal to 5.02 degrees C per mole for carbon tetrachloride, and the boiling point of carbon tetrachloride is 76.60 degrees C. Again, TB, this little TB right here, this means boiling, temperature of boiling. Okay, so its actual boiling point of the pure solvent is 76.60. I see when I made the solution, it did increase boiling point elevation. A few things to talk about through the question. First, we do have an unknown, non-volatile, non-electrolyte. Non-volatile isn't really that important when it comes to freezing point depression or boiling point elevation. It's really important when you're dealing with osmotic pressure, but it still tells me that it's something that's just going to not, randomly evaporate away before it reaches a boiling point of the solution. It's going to be, just kind of stay there as a solid. Non-electrolyte, we're going to talk more about this in just a minute, but non-electrolyte tells me that I value in my equation is equal to 1. A non-electrolyte does not break apart in solution. Electrolytes break apart. So it's like sodium chloride is a strong electrolyte. In solution, I have sodium ions and chloride ions. If I have a non-electrolyte, that would be something like, say, glucose in solution. Glucose is a non-electrolyte, so even if I dissolve it into water, it just still stays glucose. None of it breaks apart. It was prepared by dissolving 0.250 grams of an unknown in 40 grams of carbon tetrachloride. The new boiling point was 76.97 degrees C, and I want to find the molar mass. And I'm told Kb and the boiling point. So, what I want to find is molar mass. And I know molar mass is grams of solute over moles of solute. Why of solute? Because that's what I'm looking for. It's grams over moles of whatever species I'm looking for. I know that the grams of solute used here was Siri is driving me nuts today, 0.250 grams of my unknown. What I need to find is the moles. I need to find that. So I just used up this. I know that I've used that number, okay? Not that every number always is used, but I did use that number. What this is telling me is that if I put 0.250 grams into it, it causes this change in boiling point. So that number of grams correlates back to the number of particles in solution, which tells me the number of moles I have of that species. Because again, number of particles can correlate back to number of moles. Moles is a number word. So I also know I'm dealing with boiling point, and I have a boiling point elevation equation. Delta TB equals Kb times M times I. Delta TB is the difference in the boiling point. Again, in this case, it is the new boiling point, your solution boiling point, minus your boiling point of your pure solvent. But if you forget, that's okay. Just make sure you get a positive number here. That's what's important. For freezing point and boiling point, you need that value to be positive because molality will be a positive value. It will be some kind of concentration. The Kb value is given. The I value is given because, again, we'll talk about it more in just a bit. But I told you guys, if you have a non-electrolyte, your I value is equal to 1. I have enough information to find my delta TB, though. I know that my new boiling point was 76.97 degrees Celsius, and my original boiling point was 76.60 degrees Celsius. The difference between those is that delta TB. So I do the subtraction there, and I find the answer to be 0.37 degrees C. Notice this does limit my sig figs. This value is precise to the hundredths place, this value, hundredths place, this value, hundredths place. But overall, now I have 2 sig figs. So my final answer can only have 2 sig figs, okay? Or less, depending on what else is coming. Excuse me. I'm going to rearrange this equation up here, because now I have this. I'm going to rearrange the equation to solve for my molality. So my molality will be equal to delta TB over KB times I. But I just found my delta TB to be 0.37 degrees C. I know my KB, because it's given, is 5.02 degrees C per molal, and I know my I value is 1. There is no units on your Van't Hoff factor on that I value. Your units here, the delta C cancels, and the molality here is the denominator of the denominator, which makes it the numerator. When you calculate this out, you get 0.0737 molal. Notice I am carrying 1 extra digit right now for sig figs. I don't want to create round off error. I will round it at the very end, but right now I'm just going to mark where those sig figs are at. But I have my molality. I still don't have my moles of solute. But remember what molality means. Molality is equal to the number of moles of solute divided by the kilogram of solvent. What I need is right here. I have this information because I just calculated it. But I also have this information. I have this information right here. I've dissolved this in 40 grams of carbon tetrachloride. I can convert that to kilograms and find the number of moles. So my number of moles of solute will be equal to my molality times my kilograms of solvent. And I need to move the screen a little bit. My number of moles of solute is equal to 0.0737, again, marking my sig figs, molal, which again is moles of solute over kilogram of solvent. Multiply that by the kilograms of carbon tetrachloride used, because that is my solvent. 0.0400 kilograms of carbon tetrachloride. Or you can write solvent. I don't really care which one you write. Just label your stuff. Calculate this out, and I get 0.002948. But again, my sig figs are here. So I could even say 0.00295. It doesn't matter. I just know where my sig figs are. But now I can go back up and actually put that down here. 0.002948. Mark your sig figs though. Moles. So now I'm ready to actually complete the calculation and find what my goal of the question was, which is here. Do the math there, and I get a molar mass, 2 sig figs, 85 grams per mole. So the answer here to this question is 85 grams per mole. If I put 0.25 grams of this unknown, I don't know what it is, I just know it weighs 85 grams per mole, but if I put 0.250 grams of it into 40 grams of carbon tetrachloride and then boil that carbon tetrachloride, it will raise the boiling point by 0.37 degrees Celsius. What about osmotic pressure? Okay, first let's talk about what osmotic pressure is. I need you to picture this, okay? You have this system. You have a U-shaped tube here, and in the center of that U-shaped tube is this semi-permeable membrane, okay? Semi-permeable means that it allows some particles to pass through, but not other particles. It's only permeable by certain things. Initially, what I've got here is I only have water molecules on this side. And on this side, I see I have a mixture of water and solute particles. Okay? So this is a mix. And on the other side, I only have water. If your membrane, let's say in this example, the membrane is only going to let water through, but it's not going to let the solute through. Let's say the solute happens to be glucose. Okay? We can see the glucose written here. Let's say it happens to be glucose just for ease. This membrane is going to let the water molecules pass back and forth without issue. But the glucose molecules are going to get stuck and they're not going to be able to pass through. So at this picture here, at the membrane, every water molecule that hits it can pass through. Okay? No problem. But that also means if you think about the way this picture is drawn, it shows quite clearly that on the right side of the membrane, the only thing that's going to hit that membrane is water, which means that this will have 100% pass-through rate. Everything on this side can pass through. But on the left-hand side, this has at best, just what I've circled here, 4 out of 6 molecules going through, 67% pass rate. If we have 4 out of 6, so 2/3 of the molecules can go through. This is not going to have 100% pass-through rate. This, if I look right just at the surface, it's literally 1 in 3 that are going to be able to go through. The rest are going to be stopped and they can't pass through. What they can do is they can block the membrane. What happens over time is this. What we see over time is more water molecules have been able to pass this way than this way. And that's just because of the simple fact that the water can pass through either direction, but on the side with the solute, the mixture, the solute can't pass through. And so it's blocking how much can pass through. What this causes is this idea of osmosis. Or what this is this idea of osmosis, and this is what osmotic pressure is. Osmosis is the net flow of solvent molecules through a semi-permeable membrane from the less concentrated side to the more concentrated side. So the solute is going to the side of the more concentrated solution. It's more concentrated on the side that has the more particles. But that's because the solvent is the only one that can pass through. So even if there was glucose over here, there'd be less of them blocking the way. The solvent is still going to travel to the side that is more concentrated. The pressure required to prevent this from occurring is your osmotic pressure. Okay? So the process is called osmosis, but the pressure required to prevent it from happening is your osmotic pressure. So some general application uses here, osmotic pressure, reverse osmosis is actually used to clean seawater. It's called reverse osmosis because traditionally, because it flows from the side with fewer particles to more particles, we're forcing it to go the opposite direction. We're forcing water to pull out of the more concentrated side. You've also got intravenous saline solutions. You need osmolarity to not destroy the cells, especially if you're putting it into a human body. You want to put it in at the right pressure so that you're not hurting somebody or killing their cell, which could, have some serious consequences. Here's your equation. Again, I recommend just looking at the bottom one. I just need to remove the top one from my notes, but I always forget. This one, same thing. The only difference, top one doesn't include I, but you guys know to just include I at this point, whether it's electrolyte or non-electrolyte. Your properties here, the pi is your osmotic pressure in atmosphere. Capital M is your concentration and molarity. R is your gas constant in units of liter atmosphere per mole K, so 0.08206, and T is your temperature in Kelvin. I want you to recognize, though, that this is just a rearrangement of your ideal gas law, okay? So we know that PV equals nRT. All I've done here is I've divided both sides by V. When I do that, I end with P is equal to nRT over V. But these are all being multiplied divided. There's no difference in that than saying P is equal to N over V RT. Same thing. These are the same, right? This is also the same as P is equal to M RT. The only difference in the actual equation is we have changed P to be pi, and we include your Van't Hoff factor. But it is just your ideal gas law, just rearranged. Of the 4 colligative properties, osmotic pressure is the most sensitive of the different properties. So let's go ahead and work an example. Find the molar mass of an unknown protein if a solution containing 5.87 milligrams of protein in 10 mils has an osmotic pressure of 2.45 torr at 25 degrees C. For this protein, I equals 1. Now, I intentionally put this question in my notes a few years ago because I used to use it on exams, and it threw students off really badly because it's going to give us a very large number. But what I want you to think about is it is a protein. Proteins can be very large. So we're going to get a very large number here, but that's okay. That's what we expect, okay? That's also why I put it into my notes and just directly into my notes because I want students to stop being confused about that. Okay, let's think what I'm going to do here. I'm trying to find molar mass. I know it's an unknown protein. I know it contains 5.87 milligrams of the protein in 10 mils of solution. Its osmotic pressure is 0.245 torr and it's 25 degrees C and I equals 1. So I've got osmotic pressure. Pi equals MRTI. Let's see. I'm told that the pressure is 2.45 torr. I'm told that let's see, I'm not told molarity. I know my gas constant is 0.082. Siri is driving me nuts. 0.8206 liter atmosphere per mole K. I'm told my temperature is 25 degrees C. I is equal to 1. Now, my units are not matching anywhere here. I need to get my units into the same units. So I need to put this into atmospheres. I need to put this into Kelvin. Remember to put it into atmospheres, 2.54 torr, 1 atmosphere, if 760 torr, which is 0.00322 atmospheres. So I've got 0.0032, 0.00322, that's hard to say, atmosphere is equal. I don't know my molarity. It's probably what I'm going to try to find. I know my gas constant, 0.08206 liter atmosphere per mole K. I know my 25 degrees C. If I convert that over, that becomes 298 K. And my Van't Hoff factor is 1 because it told me I is equal to 1. Okay? So I've got all that. Now let's rearrange this equation. What I'm trying to solve for is my molarity. My molarity is equal to my pressure. Again, I just moved them around. I know it confuses some students. I take this, okay, and I'm going to divide both sides by this to isolate it away from the M. I just like my M on the other side, which is why I did this. So my molarity is equal to my pressure divided by RTI. And that's what I have here. Make sure your units cancel. Atmospheres and atmospheres. Let's see, Kelvin to Kelvin. And I've got liters per mole in my denominator. That make the liters stays in the denominator. The moles is the denominator of the denominator. So that brings to the numerator, which means I get moles per liter, which is the correct units for molarity. And I see my molarity here is 1.32 10 to the negative 4 molar. But that's not answering my whole question, right? That's only giving me part of it. This is moles per liter of solution. What am I going to do now? Well, what do I really want to know? I want to know molar mass. So I really want to know how many grams I have to how many moles I have. And I'm going to move this over. I really want to know number of grams of the protein. We're going to just call it P for protein. I don't feel like writing it all out. Number of moles of protein. I know that this contains 1.32 times 10 to the negative 4 moles per liter of solution. Well, that's not going to help me. My moles are on the wrong side here. I might have to flip that around somehow. I'm also told I have 5.87 milligrams of protein, so this is protein, over 10 mils of protein. Both are conversion factors. I don't truly care which one you start with. I'm going to go ahead and move this one out of the way. Because again, this one isn't going to help me. I've got the moles on the wrong side, so I'm going to have to flip this equation around at some point. I'm going to go ahead and start with this one. 5.87 milligrams of protein. I could start with the other one as well. It doesn't matter. I'll show you that in a sec. But 5.87 milligrams of protein for every 10 mils of solution. Because it's dissolved into the solution. I want grams of protein. Well, I know that 1 gram of protein contains 1,000 milligrams protein. So that cancels those units, and I get my grams. Now I just got to worry about that denominator. I've got 10 mils of solution here. I've got molarity here, but it's in liters. I'm going to have to get those units to cancel out somehow. So I know that there is 1,000 mils in every 1 liter of solution. My mils cancel out, and I'm in liters. Now I'm going to use that density, that molarity. 1 liter of solution contains 1.32 10 to the minus 4th moles of the protein. And you should get an answer of 4447. I'll talk about sig figs in a sec, grams per mole. So again, liters of solution have canceled. I've got grams per mole of protein. I've got 3 sig figs here, and 3 sig figs here, and 3 sig figs here. So my sig figs here, 4450 grams per mole. And that is the correct answer. But let's talk about if I had started with the molarity instead. Again, I know I'm trying to get to grams per mole because I want the molar mass. So I need number of grams of protein over number of moles of protein. Some students aren't going to be comfortable starting with that 5.87 milligrams per 10 mils of solution because they're just not going to see it. That's fine. You can start with your molarity. That's what you just solved for. But notice here, I need my moles of protein in my denominator. Students have a hard time remembering that you can flip molarity around because it is just a conversion factor. But you do have to do that. We saw that we saw it when we worked it out this way as well. I know for every 1 liter of solution, I have 1.32 10 to the minus 4th moles of protein because I solved that from the osmotic pressure. So now I've got my moles set, but I need to try to figure out how to get grams in the numerator. The only other information I have about that solution is this 5.87 milligrams of protein per 10 mils. That should say 10 mils of solution, but it does say if a solution containing this. So it kind of hints at it. I'll try to remember to fix that. But that's mils to liters. I know that I don't have a conversion there. So I know, but I do know that 1,000 mils is 1 liter. So that converts my liters for me. It tells me that every 10 mils of solution contains 5.87 milligrams of the protein. That cancels my mils of solution. Now I'm really close. I'm in milligrams, but I want grams. So now I can just say, well, I know that 1 gram is 1,000 milligrams. And I will get the same answer, the 4450 grams per mole. I don't truly care which way you do it, as long as you understand why you're doing it, okay? I know this gets pretty messy on these slides. I apologize. The slides are to percent in class, not to write all over. But I hope that makes sense. But again, it is a big number, and students kind of get freaked out by that, but it's a big number because it is a protein, and proteins can be large. They don't have to be, but they can be. Okay, what about colligative properties of electrolyte solutions? I keep talking about the Van't Hoff Factor and alluding to it, but I haven't just described it yet. Colligative properties, again, are properties of solutions that depend on the number of solute particles, but not on their identity. Just depends on how many are present. Strong electrolytes we talked about in first semester. Strong electrolytes are things that break apart entirely in solution. We have strong electrolytes, weak electrolytes, and non-electrolytes. Remember, your strong electrolytes are your soluble salts, strong acids, and strong bases. So your soluble salts come from your solubility rules. Your strong acids you should have memorized. Your strong bases you should have memorized. Your acids, HCl, HBr, HI, HClO3, HClO4, H2SO4, HNO3. Your bases, I usually do off the periodic table. So 1 second while I pull one up, because I have them pretty much memorized, but I find them off the table faster. So, and you will always have a table to do it. Lithium hydroxide, sodium hydroxide, potassium hydroxide. Let's see, rubidium and cesium. And then you've got your calcium hydroxide. Your barium hydroxide is slightly lower. Barium hydroxide. And your strontium hydroxide. Okay? So remember, your bases form a B on the periodic table. They form like a B shape. And that did not work. And there's 8 of them. 7 acids, 8 bases. Okay? And remember, these 3 break apart into 3 things each. The coloring on this background is not going to let me highlight very well. These each break into 2 things. These each break into 3 things. Okay? Your acids each break into 2 things. Sulfuric is a special case. The second proton lost isn't lost very easily. Up until now, and then your soluble salts you need to know, and you need to recognize how they break apart. Weak electrolytes only break apart slightly. Non-electrolytes don't break apart at all. So up until now, we have focused on the colligative properties of non-electrolyte solutions. For electrolyte solutions, we have to take this into account, which to account for the total number of particles in the solution. And this is where that Van't Hoff factor, or I, comes into play. So Van't Hoff factor is an ion pairing. You can calculate it, but it's just easier to do the theoretical, which is just how many particles it's going to split up into. Your non-electrolyte, look here, we've got non-electrolyte, sodium chloride, magnesium sulfate, magnesium chloride, potassium sulfate, and iron 3 chloride. And we can see our expected value versus our measured value. These are all being prepared in a 0.05 mol concentration. Non-electrolyte expected has a Van't Hoff factor of 1 and a measured value of 1. Sodium chloride has an expected value of 2. Why? Because it splits into 2 things. It splits into sodium ions and chloride ions. Magnesium sulfate, again, splits into 2 things. Magnesium ions and sulfate ions. Magnesium chloride splits into 3 things. A magnesium ion and 2 separate chloride ions. Potassium sulfate splits into 2 separate potassium ions and 1 sulfate ion. And iron 3 chloride splits into an iron 3 plus and then 3 chloride ions. So hence the value of 4. Now, what we actually see theoretically ends up being smaller than what we expect, and this is due to ion pairing. Basically, this is what's showing down here in solution. We say that the particles are completely segregated away from themselves. So we say like the chlorine here, the chloride, Cl minus, and the sodium, Na plus. We say they're so far from each other that they're not associating with each other anymore, but that's not quite true. They, depending on how concentrated the solution is, they do pair up, okay? So there is some what we call ion pairing. I is almost always less than what we would expect it to be because we assume complete dissociation. In the real world, things don't always completely dissociate. So the Van't Hoff factor, I, approaches its ideal value, what I would expect it to split up into, as it approaches infinite dilution. So for example, the Van't Hoff factor for a 0.05 molar NaCl solution is 1.9. We got that on the previous slide. What would the Van't Hoff factor be for a solution that is 0.5 molar? I don't know its exact value, but I know that it will be greater it'll be less than 1.9, maybe 1.8, maybe 1.7, maybe 1.85. I don't know. But this is more concentrated. So there's more ion pairing. What about the value for 0.050? Molal. Sorry, it is molal here because we're lowercase m. I know that it will be somewhere between 1.9 and 2. It's probably still going to pair up a little bit, but the closer it gets to dilution, the closer it gets to 2. If you know the value of I for one colligative property, it's the same value for all the colligative properties. Now, theoretically, if we just pick it based on its idealized value, that's when we just look at the particles splitting apart and what it should be. What I mean by if you know it for one, you can use it for the others is if I actually have the experimental information to calculate the Van't Hoff factor for one system, I can use it. If, like, say I find it experimentally on freezing point depression, I can use that same I value if I want to go ahead and do the boiling point elevation for that same solution. The Van't Hoff factor stays constant for the solution itself. Why does that Van't Hoff factor deviate at higher concentrations, though? It deviates because of ion pairing. The ions are interacting with each other. Even though we assume infinite dilution, they're still interacting, they're still together, and so they're not fully breaking apart like we would expect them to. So given that the Kf value for water is 1.86 degrees C per mol, let's talk about a few examples here. Determine the freezing point of 1 mol of glucose. Glucose is a non-volatile non-electrolyte. When you have a non-electrolyte, I equals 1. No exceptions. I equals 1. Because it doesn't split up into anything, okay? Delta Tf is equal to Kf times m times I. Delta Tf is equal to 1.86 degrees C per mol times a 1 mol solution times 1. Notice here the answer of the equation is 1.86 degrees C, but that's not the answer to the question. This is freezing point. All I've done so far is calculate the change in the freezing point. The actual freezing point of the solution, water freezes at 0 degrees C, so the freezing point is negative 1.86 degrees C. I have to subtract that from the actual freezing point to get its actual freezing point of the solution. The freezing point of 1 mol solution of sodium chloride, assuming complete dissociation. What would this be? Well, I know sodium chloride is NaCl. I know this splits up into Na plus and Cl minus ions. So I know my I value here is equal to 2. My delta Tf, 1.86 degrees C per mol times 1 mol times the value of 2 gives me 3.72 degrees C. But again, that is only the change in freezing point. My actual freezing point is the freezing point of water minus this value. So Tf is equal to negative 3.72 degrees C. And what is the freezing point of a 1 mol solution of magnesium chloride assuming complete dissociation? Magnesium chloride is MgCl2, which splits up into Mg2 plus ions and 2 moles of Cl minus ions. So delta Tf is equal 1.86 degrees C per mol times 1 mol times 3. It says an I value of 3, it splits up into 3 things. This is 5.58 degrees C, but again, that's subtracting it from water, from the freezing point of water. The freezing point of the solution will be negative 5.58 degrees Celsius. So again, negative 1.86, negative 0.372, and negative 5.58. What I find is it didn't matter what the solute was. It just mattered how many particles it was that was causing that solution to get more and more depressed, more and more, lowered more and more. So assuming complete dissociation, which of the aqueous solutions below is expected to have the highest boiling point? Well, let's see. Let's talk through it. To do a question like this, you need to think about the Van't Hoff factor first, and then think about concentration, okay? Boiling point is delta TB KB times M times I. I could go ahead and calculate all of these, yes, but KB is a constant, okay? So that is a constant, so if I just take my molality times my I value, the biggest value here is going to cause the biggest deviation on what I'm doing. I here is equal to 1, which means overall this will be 0.080, and the value I'm writing over here is your molality times your I value, okay? Sodium phosphate, that splits up into 3 sodium ions and 1 phosphate ion, so I is equal to 4. 4 times 0.06 is 0.24. KCN, potassium cyanide, sorry, I'm trying to move the screen. Potassium cyanide splits up into 1 potassium ion and 1 cyanide ion, is a polyatomic there. I is equal to 2. It does not split up into 3 things. Remember, it splits up into K plus and Cn minus. That is a polyatomic cyanide. 2 times 0.15 gives me 0.30. Lithium perchlorate, that 4 should be superscripted. I apologize for that. It should be. Definitely did not catch that. We'll try to remember to fix that. Lithium perchlorate, again, this splits up into lithium ions and perchlorate ions. So my I value here is equal to 2. 2 times 0.1 is 0.20. So you're going to have to know your polyatomics to do these things. And then magnesium nitrate splits up into 3 things. I is equal to 3. Splits up into Mg2 plus and 2 nitrates. So 3 times 0.12 gives me 0.36, okay? So I want to know which one will have the highest boiling point. Remember, it's boiling point elevation, which means the greater deviation here, the greater here, the greater value that's added. These are all aqueous, which means it's all added to 100 degrees C, okay? Whichever one's being added that's biggest is going to cause the highest boiling point. So this value is the highest. This is going to cause the highest boiling point. Which one would cause the lowest boiling point? It is boiling point elevation, so I want the one that causes the smallest addition to the boiling point. That will be the smallest number. In that case, A. Freezing point. It is called freezing point depression. So if water freezes at 0 degrees C, I want it, and the bigger it is, the more it's going to lower that number. The smaller it is, the less it's going to lower that number. So the highest freezing point is the one closest to the real value. It lowers it the least, and that is A. The lowest freezing point is the one that's going to lower it the most, the greatest deviation, and that is E, because of the most particles. Vapor pressure goes along with boiling point. Remember, vapor pressure or boiling point is due to vapor pressure. So the higher the vapor pressure means more particles can escape. Causing a higher vapor pressure. That means I have less particles in solution holding these things back, so therefore it's able to escape. The less particles would be A. The lowest vapor pressure means the fewest particles escaped. Most particles are kept back in solution, so that's the one with the most particles. Osmotic pressure. The high osmotic pressure, remember P equals MRT times I. R and T are constants here. If I'm doing them at the same temperature, I'm measuring what this is going to happen. It's going to be the most concentrated. to have that highest osmotic pressure. It's going to be the least concentrated to have that lowest osmotic pressure. Okay, now this definitely helps more on the previous portion of the chapter, the solutions chapter, but some helpful assumptions when you're working cumulative problems, because you can see cumulative problems again with colligative properties as well. If you're given mass percent, assume you have 100 grams. Now I want to emphasize that. When I write things like M over M, let's say I say you've got something that's 85% M over M, or I say 85 M over M percent, whichever way I write it. You assume you have 85 grams of the solute to 100 grams of the total solution. Again, your solution is your solute plus your solvent, okay? So if you see M over M, it's grams to grams. Grams of solute to grams of solution. There's not enough room for me to write on this page. If you see, so M over M, if you see M over V, 85 grams, or whatever the value may be, of solute to 100 mils of solution. And if you see V over V, 85 mils of solute to 100 mils of solution. And really the reason we use the different ones is because how we measure it in lab. Sometimes it's easier to just measure mass, sometimes it's just easier to measure volume. But if you see percent, look at what I told you. Is it M over M, M over V, or V over V? If it's M over M, it's mass of solute to mass of total solution, which is solute plus solvent. If it's M over V, it's mass of solute to volume to milliliters to 100 mils of solution. And if it's V over V, it's mils of solute to mils of solution. But assume everything's out of 100. That way the percent you're given is the numerator, and then you should assume 100 for the denominator. If you're told, 85%, that is two sig figs. Assume your 100 is to the same precision. If you are told 85.0, assume 100.0 so that they're precise to the same value, okay? If you're given molarity, assume you're given 1 liter of solution. So let's say I told you that you have something that's 2.5 molar. Well, if you assume 1 liter, then you have 2.5 moles. And if you're given molality, assume 1 kilogram. If I told you 2.5 molal, and you assumed 1 kilogram, now you have 2.5 moles as well. But again, that is solution versus solvent. You've got to keep those straight, okay?